Hi, this is Lisa Knight, and this is Lecture 11, and we will be talking about equipotential lines and capacitance. So, let's just review something that we kind of have some familiarity with, and that's maps. If you've ever done any kind of hiking or anything that required that you use a topographic map, this image or type of image may be very familiar to you. When you look at this topographic map, you see all these lines. Each line represents an area of equal elevation. So on tab hill here, we have the top of the hill's elevation here. And then you notice that there's one side where the lines are closer to each other and one side where they are further apart. This is a shallower sloping side and a side where it's very steep. The contour lines are very close to each other. Once again, each contour represents a specific elevation, and if you walk along that contour, you will always be on that particular elevation. We can represent the voltage around a point charge in a similar way. So imagine that you have a point charge, a positive point charge, and remember that the electric field lines radiate away from it. And if you were to measure, say, 3 inches out on any one of the lines and measure the voltage there would be 1 volt in this case. Anywhere 3 inches out, the voltage will be 1 volt. And if you made a mark at the 1 volt mark everywhere around this point charge where it was 1 volts from the point charge, you would see that if you connected the dots, it would make a circular line. This is like a contour line, but instead of representing elevation, it's representing the voltage around that point. And remember that field lines point in the direction of decreasing electric potential. So as you go away from it, the voltage gets less. But as you come in against the arrows of the electric field, the direction of the electric field, the voltage is greater. Notice that when the electric potential lines are very, very close to each other, the field is also very, very strong. And when the electric potential surfaces are very far apart, then the field is very weak, indicated by the great distance between the field lines. When you have combinations of charges, you can use the equipotential surfaces to construct the field lines between them, because the field lines are going to be a little more complicated. So what you can do is you can find areas of equal voltage and draw a line through it representing equal potential. And it turns out that by definition, equipotential surfaces are always perpendicular to the field lines. So, for example, looking at our dipole here, at the negative side of it, we have our equipotential surfaces, drawn. And you notice that the field lines start at the charge and they go through, and you see that they are hitting those round equipotential surfaces at right angles. And for the field lines that are out further, you can see that as they go out, they have to bend in order to hit those field lines at right angles. When we think about conductors, which are materials that allow electrons to flow, we think of them as acting like an equipotential surface, which means that if you have a spherical conductor, or any conductor, no matter what its shape, that the charge does not accumulate throughout it. It accumulates on the outside of it only. So that means you could stand inside of this conductor, and even though it's conducting electricity on its surface, the interior is just fine and you would be safe. And because it's conducting electricity and conducting electrons just along its surface, it acts like an equipotential surface itself at a certain voltage. The conductor that has more of a curve has a higher or stronger electric field because it simply has more charge on it. And it's important to note that this idea of electric potential and electric fields is important. Many of you are going to study medicine or go into something related to it, and it's very important to remember that we utilize the fact that there are electric fields inside the human body to be able to understand it and to figure out if there are things wrong with it. For example, an electrocardiograph plots the heart's electrical activity, and an electroencephalogram measures the electrical activity of the brain. Now, let's move on and talk about one more concept, the concept of the capacitor. The capacitor is a device that stores charge in the form of Q. In the simplest capacitor is a parallel plate capacitor that is separated, two plates, one positive, one negative, separated by a finite distance d. The capacitance of the capacitor is related to both the charge and the potential difference on the capacitive plates. Imagine that if I had more voltage here, I could hold more charge. And if I had a bigger plate, I could hold more charge. So capacitance is a measure of how many coulombs per volt a capacitor can hold. And it's measured by the charge on the capacitor plates divided by the voltage between them. It's measured in farads, which are coulombs per volt. By calculating the electric field in between two parallel plate capacitors, we can modify our equation a little bit. And we find that instead of just when we don't know the charge on the capacitor, okay, then as long as we know how strong the field is, how much area the plates have, and we know a constant called the permittivity of free space, we can simply calculate the capacitance using the permittivity of free space, which you look up in your book, and the area in meters squared of a plate divided by the distance between them, and that can also give you the capacitance. The capacitance will increase as the plates become larger. Right? So the bigger these plates are, the more capacitance. And the closer together the plates are, the more capacitance. It's an inverse relationship with distance. A dielectric is an insulator, and when placed between the plates of a capacitor, it gives a lower potential difference for the same charge. And due to the polarization of the material, this will also increase the capacitance. So a lot of modern day capacitors are not pieces of metal separated. They're actually like a sheet of thin metal, aluminum or gold, and in between them is a sheet of paper or a sheet of mica or some dielectric material. The polarization of the dielectric results in a lower electric field within it. So it has a new field, E naught, and it's related to something called the dielectric constant, K, which is something that you would look up for the particular dielectric that's between the capacitors. And with that in mind, then if we look at this, we can modify our capacitance equation to include to describe a capacitor that has a dielectric in it to be K times Q all over the initial voltage. Just to give you an idea of some of the dielectric constants, like water is a very big dielectric constant, but Teflon and air has a and a vacuum has the smallest dielectric constant. If the electric field in a dielectric becomes too large, it can tear the electrons off the atoms, thereby enabling the material to actually conduct. So this is called a dielectric breakdown. And the field at which this happens is called the dielectric strength. So this tells you how basically the limits of these particular common dielectric materials. Because you don't want them to conduct material. You want them to promote charge storage, not to conduct the charge off of the capacitor. All right, that concludes our discussion of capacitors. Our next lectures will start to turn and focus on circuits, and I'll see you then.